Welcome. Good morning. Welcome to the sixth CSL Student Conference. It's been a long time since I was a student in CSL, so I feel a little bit awkward giving the welcome. But since I have been here for the past 5 student conferences, I thought I'd just say some words about the conference. So first of all, it's purely student-initiated, student-run, student-organized. Faculty don't do anything. So it's like the #1 rule, and it either succeeds or fails on the basis of the student ability to organize, and I've been very impressed. They've been doing a really good job. Some of the past organizers are out in the workforce. I saw Shreyas Sundaraman. Yeah. So 3 years ago, he was the head organizer. I saw him at the CDC conference, and he was looking at the website and very interested in how things are going. And I'm sure he's applying skills he learned when he was organizing here. And many of you will be out there in the workforce in 2 or 3 years. So this is a great way. You have to reach out to the world and see, not just look at what your research is for your thesis, but decide what are the hot topics going. Who should we invite to come to the conference? And you learn how to work with each other and organize, and it's really good. Well, I've been impressed. I think we should all thank the CSL support staff, like Dan Jordan, the building manager, and some of the secretaries, because sometimes at the last moment with new organizers, Dan was telling me about a phone call he got on Sunday. So we should just recognize them for their support in this also. And I think that's all I want to say. So Rami will be introducing the speaker. Thank you.
Thanks a lot, Rami. That was a good memorization. I'm impressed that you didn't have to look at that at all. And thanks for having me here. I enjoy coming here, and I usually come in when it's cold, so I'm okay. I went to Syracuse University, and it's about the same. So. So this is a real hot topic in the industry today. In fact, President Obama mentioned this, that clean energy is a priority in the United States, but also in the rest of the world. And so I wanted to tell you today what TI is doing and how our products sort of map into this type of these types of applications. And then one area in particular that we are involved in, which is a really hot topic in the world now, is power line communications. How can we communicate between meters outside your home, electric meters, and to the utility grid? It's really tough to do that, and I'll talk a little bit about the challenges. So I'll talk a little bit about TI at the beginning and where we're at, and then talk about the application over the grid, and then talk about what we're doing in TI as far as our solutions that we are applying to this type of application. And then talk about standards. Standards are important, and it's been like the Wild West over the last several years. A lot of proprietary things out, but we're finally getting things organized. And I'll talk a lot about that. We have to go out and do a lot of field trials to understand these tough communication channels that we have to operate over. And there hasn't been enough of that done in the past, and we understand a lot of the challenges now and believe that it really is possible to do this very reliably, even communicating through transformers outside your home. Talk a little bit about our products that we believe are the most relevant to like fueling this market initially, and then I'll just summarize at the end. So this is a 2009 slide, but we just had our 2010 report. But what it does is it shows four big segments in TI, and you notice in red analog is a big segment. So 4.2 billion out of 10 billion was related to that. And one of the things I mentioned is that analog is not all analog. There's a lot of digital in analog too. Controllers and things like that. Power management, for example, it has controllers in there to optimize the the efficiency of these power supplies. And then embedded processing, that can include DSPs and microcontrollers and all kinds of things, and that's really a nice business inside of TI, video, consumer, all kinds of applications. Motor control is one big hot topic now inside of TI. And then wireless is there. We've done a lot of work with wireless. And then there's other activities like DLP and our consumer calculators business. So we just had our report for 2010, and so I superimposed that, and you can see analog grew pretty much, quite a bit, and then our revenue grew about 38% last year. So TI is doing pretty good, 32% profitability, and so lots of good opportunities there. We seem to be in the right kind of businesses, and you can see the embedded processing is another emphasis, and we had really good growth there. And so here's a sort of a block diagram of all the pieces that TI, it's sort of generic, sells, and we try to sell all the analog front-end circuitry for sensor interfaces and A to D converters and things like that. Low power RF is an emphasis for Zigbee type applications, and embedded processing I mentioned, and all these other things. And so these are products that really map into smart grid type applications. And we have a variety of microcontrollers there. The MSP430 is a really low power microcontroller that's used in meters for metrology, measuring current and things like that. And it's used very widely in the industry, in universities, and for all kinds of applications. C2000 is what we actually have our power line modem running on. It's a 32-bit processor, and we sell that into motor control applications too. And then we have ARM Cortex M3 products, and then we have this OMAP L1X, which is an ARM with a high-speed C6000 in it. So we tend to use that more in like concentrator type applications where there's really a lot of computation to be done. And it runs Linux and all kinds of different operating systems. And so, and then we have the complementary analog products that we use. And let's see if I can find the button. This one is very important in power line communications. These line drivers, they have to sink 10 amps of power, and they get really hot. And TI is a leader in that kind of product. And so this is one of our actually this line driver technology comes out of Burr Brown, one of our acquisitions, is a big differentiator for TI. So I'm managing that group, and so we have the Systems and Application Center in Dallas, and we support all these business units in some way or another. And in the case of power line communication, we have our MCUs here, embedded processors, and then we have these products. So we're working with both of these organizations. So we're doing the systems work, and so they provide the products, and we tell them, well, you really need to do this or that to these products to make it marketable and affordable to the industry. And we also work on wireless body area network, personal area network, like Zigbee and things like that, Bluetooth, neighborhood area network, and wide area network. That could be like WiMAX. And so we've had products in all these areas before. We do work in GPS for indoor positioning, integrating different types of sensors. So I'm going to go over this quick. I think maybe you've all seen this. This is from NIST, and it's existed for 2 or 3 years now. But I wanted to just say that why is TI interested in this? And it's because 60% of the semiconductors in the smart grid are related to premise type technology. So appliances, meters, consumer equipment, electric vehicle, and that type of thing. And then we have semiconductors that are used out on the power lines to measure the quality of power, that type of thing. Here's a home and a neighborhood, and we're involved in all of this, in selling semiconductors into like smart appliances and gateways and smart meters and the electric car. This is the standard for the cable between the electric vehicle and the charging station. And so we're involved in the definition of that, actually, we were. And then we're especially involved in the communication standard that's used to communicate from the electric vehicle to the utility via this cord set. And we actually just, this past week, we submitted a document to the SAE to be considered. And then there's the neighborhood area network, and there's a variety of ways to get this data back to the utility, and it's not totally, there's not one way to do it. There's many ways to do it, and it's sort of utility dependent at this time. So here's a simplified power grid. You have a distribution substation, and we all know what that looks like. And then we have high voltage lines coming in and medium voltage lines coming out. These might be 7,200 volts. And then we have the low voltage lines here. Going to the home and the meter. So we have power line modems that operate strictly over the low voltage lines. It's a little bit easier to do that because the distances are a lot less. But we really need to operate from the meter through this transformer, which is makes it really tough to do, to the medium voltage lines. And so we have to couple our modem to these medium voltage lines and go through the transformer. It makes it particularly difficult to do that. And then at a substation, you could have 50,000 or more meters associated with say a concentrator there. So you have to do a lot of networking besides. So there's some networking work to do, and then also the power line communication over this network is pretty tough, and so it's like a research problem, actually. And in my view, it's not solved yet. So we have point solutions out there. We've seen these things deployed, but do they work? Well, they work in some cases, but you want to have 100% connectivity to every meter, and so how are you going to do that? So we can help to do that.
Excuse me. So there was some problem using wireless, right, for that part, from the home to the...
So that's true. So there's different alternatives. In the United States, there's a lot of that right now, the RF mesh networks, and so they don't communicate over the power line. But there are applications, there are utilities that are using power line. Also, like Duke Energy and some other utilities are using power lines. So it varies. Yeah.
I don't want to deter you from moving forward, but one of the biggest challenges I've heard of using power line is that the meter might have trouble reporting an outage because it might be the power line that's broke.
Yeah.
Are you thinking about how to deal with that problem?
Well, you can have backup systems, so you could have both in a meter, that type of thing. And so we may not, TI might not solve that problem actually, but we can provide the means to solve the problem. And so it's a solvable problem, right? And so it's just how do you do it, right? What's your backup if your power line is not working, and then how do you get that information back? Perhaps maybe through the internet in your home, or some other way through a RF mesh networking capability. Yeah, but that's an issue. Yeah. I think that just recently came up as an issue. remember reading something recently. So in our solution, we have this C2000, or this is F2000 because it's got flash memory, and C is not flash. And so F just means that there's flash memory in it. And it has the A to D and D to A converters on it. And we provide a software stack, including the modem. And we actually certify this with certification labs. And so what we do is we actually provide this software library. It's been certified using our evaluation module. So this is not the end product. The end product we would have a customer take this and then do one board, and it might be like that, small communication module. And it would all fit onto the communication module. We just sort of put these things together as Lego building blocks, so that any customer can take them and do whatever they want with them, and the software too. And then we have an integrated front end, has the driver and the receiver integrated on it. Here's a chip right there. It came out of the fab late last year, and we tested it out in our group and verified that it works over the full temperature range too. And then you have a coupling circuit. And so the coupling circuit is pretty important too. So if you look at the communication channel, you have to communicate over the channel, which includes the front end, the coupling circuit, and maybe a couple other coupling circuits on the line over the medium voltage lines and that type of thing. So you have to consider all of that. The transformer, you're communicating through a transformer. And so and transformers are different too. So it depends on who you buy them from. So power line communication in Europe, though, I mean, they're using power line communication in Europe, deploying that. Not so much RF mesh there. So our initial focus is in Europe, and so there's some fairly widespread deployments going on there, and I'll discuss that. U.S. more RF. Japan power line. They don't seem to like RF there, so it just varies on what country you're in. And then here's an EVM. I'm going to just skip over this, but this is where we have our modem there, and then this is the OMAP L138, which is that processor I mentioned that has Linux and the C6000 in it. So, and that would be used for, say, concentrator type applications, or determining what the quality of the power is on the grid. There's lots of work being done on that also. So standards. Standards is important. And why are they important? Because customers want to have multiple suppliers, multiple chipsets that they can buy. And it fuels competition. It also drives you have to have some way to certify your equipment, test it, and verify that it performs to certain standards. And so that's why standards are important. And then the devices from different companies have to coexist and even interoperate with one another, communicate with one another, so you need a standard. Ideally, these companies are sharing the R&D burden. As we're developing the standard, they're doing their own experiments, and then we put it all together, and then we agree. Of course, there's a lot of fighting in the standards too, so it's fighting and cooperation and hopefully getting to what you need for the market. And then customers are involved on that, like utilities are involved in the standards, and they provide requirements, and they can say, well, we don't like this or we don't like that. I'm going to talk about existing PLC technologies that are being used now. And so for the consumer application, we have HomePlug, and that's part of the IEEE P1901 standard. So it is standardized in the IEEE now. And then there's an ITU standard, which is slightly different, G.HN. HN is for home networking. And they operate over 100 megabit per second in the home, built into set-top boxes and routers and things like that, as a backup to Wi-Fi. sometimes. And then by the smart grid, I mean this is really outdoors. So we're focused on OFDM technology. And the technologies in Europe, which we're using as a basis for the new IEEE standards, are called Prime and G3. And Prime is in Spain, G3 is in France, and G3 seems to be the one that is the favored one because it's more robust in some of these environments. And then we have some low bit rate standards that exist. The standards that are in progress now are in the ITU and the IEEE, and TI helped to found this effort back at the Globecom meeting in December 2009, and now it's really rolling. We have a lot of companies that are involved in that, good representation from a good cross-section of the industry, and we should have a draft document in the February-March timeframe for this. And we're involved in this one too, in the ITU. They're very similar, and we'll have a draft document in February for that one, and somehow we have to figure out how to merge those, which is going to be tough. We can go up to megabit per second. We operate up to 500 kilohertz, call that the FCC band. And then we want it to be used in rural and urban communications. You have to use IPv6 and some of the more advanced networking technologies. And networking is a challenge here because you have to, there might be meters that the concentrator doesn't necessarily see all the meters there. So we have to form a mesh. And so how do you form that mesh? And the mesh can vary because line impedances change with time, the channel changes with time, and so a meter might disappear, okay, but you have to be able to handle that situation. So that's actually built into the standards on how you handle that. And then security is very important, and I'm not going to talk about that too much today, but that's important. And it has to operate over DC and AC power lines. So the charger, the charging station might deliver DC in the fast charging case for the electric vehicle. Okay. And field trials, as I mentioned before, are really important. So I'm not going to really go through this, but this is a block diagram of the G3 phi-layer functional flow, and it's contained in my slides, so you can look it over.
What sort of distances are we talking about from the meters to the concentrators, the worst case?
So in rural applications, it could be actually 100 miles. But that's very low bit rate stuff. And typically, you know, we're talking about, in Europe, they're talking about maybe 3 kilometers to the distribution substation, something like that, so more in the urban type areas. And so you'd be able to transmit at higher bit rates in that particular case. There's some, the very low bit rate stuff is proprietary now, but they're the companies that have that are involved in the IEEE.
Thanks. I had 2 questions.
Okay.
So, first, why is that before there's difficulty if you go through a transformer, right? What makes it difficult?
Well, because you don't really know exactly what the transfer function is through the transformer. It's just sort of like not well controlled. I mean,
it's changing a lot? Or?
Well, it's different. The transformers are different, and so you buy a transformer for because they don't care about communicating through it. And so we found that different transformers have different transfer functions. They act like a low-pass filter. Really, I mean that's sort of the big thing. They're like a low-pass filter, but there's also some resonances that go on in there. I mean, it's just sort of we haven't really fully characterized these transformers yet, and it may be difficult to do that. I mean, it may just require we operate over the different grids, and then adapt the modem to that particular grid, and it has to be adaptive. And so we sort of know what the transformer does, but they're different, and so we don't know exactly what it does. That's one of the challenges. And these coupling circuits, you buy those from different companies. To the medium voltage lines, they're all different too. So it's like lots of opportunities for some research, really.
And another question I had was like, what kind of communication are you thinking of having over the power line? Is it more like the information from meter to meter, or is it like replacing the internet, replacing the communication?
It's not internet. It's low bit rate. It'll be low bit rate, 10 kilobits per second or something like that. So it's two-way communication now. But AMR is meter reading. One-way communication is sort of taking place now. In fact, you have trucks that drive by and they just sort of read your meter. It's about a couple hundred bytes of information, and so we want to communicate that information and their standards. So you can go to a standard and find out what that information is, and so the utilities want to read that information, but they want to also be able to communicate back. And so that's what we're doing here. But typically, it's going to be very low bit rate. And they might want to read a meter maybe every 15 minutes or something like that.
I guess the problem is that it's just not possible to have higher bit rates, right? Because
No.
once there would be higher bit rates, you could have, right?
That's not possible. No. Unless you have a circuit that bypasses that transformer and goes directly onto the medium voltage lines, which they tend not to want to do. Just put the meter in and it talks to the substation is the ideal solution. And then we're talking about different bands. These are in Europe. Senelec A band is owned by the utilities. It's from 9 to 95 kilohertz about. And that's the band we use in Europe. But these are usable by consumer equipment, and then there's the FCC band on top of that, which is above that. This is the upper frequency on the D band is 148.5 kilohertz. So these are the standards I mentioned. They're deploying 100,000 meters with this prime technology in it this year in Spain, and it's just on the house side of the distribution transformer. It's cost effective because in Spain they typically have 100 meters connected to a transformer. So you can put a concentrator at the transformer and it's cost effective. In the US it's more like 1 to 3 homes are connected to a transformer. Not so cost effective to do that. In France they're going to deploy about 2,000 meters this year with the G3 technology. They're both OFDM technologies. And they require going through the medium voltage transformer. And the topology is similar to the US, so not so many meters attached to a transformer. And then these are going to be used as a basis for these international standards. And then we're working with this is the document J2931-3 that we just submitted to the SAE. It's our low-frequency narrowband OFDM power line communication proposal. Well, this is a little bit more benign type environment than transmitting outdoors through transformers and that type of thing. So this is more straightforward. So real quick, go through, we went to Spain, and this is in Madrid, and green is good, so those green stars are good. We just had a concentrator in the meter room shown here, and that's a typical meter room there. And then we put modems at these different locations, and then this is where we had like the concentrator here. So we had a concentrator, and then we had modems at these different locations, and they just connected up, and they transmitted at the full bit rate, which was 64 kilobits per second with the coding and everything. This one didn't connect right away, and it wouldn't talk to the concentrator, but the standard allows you this to find a friend, basically, and then it automatically discovers a way to communicate back here. And so everything worked pretty good. Switch node is like a repeater. And then in France, I didn't do these slides, but this was done maybe a couple of years ago. They're communicating over medium voltage lines, and here's some examples here. And we have different communications technologies that we're trying out here, and this is actually the G3 technology here. And so you were able to communicate fairly well using that technology. But I mean, by now it's better. This is a couple years ago. But you can see the bit rates that we're talking about here, not super high bit rates. So you're not going to use this for internet access. And then this was near St. Louis. We did a field trial this summer, and you know, we have modems that somebody from the utility has to be there, and then we were working with a meter manufacturer, and then we went and we connected our modems up, and we measured how well they communicated, and then we had portable spectrum analyzers. We recorded the noise at each one of these locations here, and so it's very tedious, but you have to sort of do that. This is a coupler that we used here to couple to the medium voltage lines, and had somebody sitting under the tree for a few hours. And this is how we take the noise measurements, and with our spectrum analyzer, we bring that back to Dallas, and then we integrate it all with our MATLAB simulations. We're also looking at okay, so in some cases, these modems wouldn't connect. Well, what's the problem? And so we found that, well, we really need to sort of be looking at subbands and sort of scanning. So we have to scan up and down. We always found a band that worked. There was always a band that worked. And it seemed like 42 or so, we picked that number for a reason. Kilohertz band was ideal. But we could go a little bit higher than that. And one of the reasons why we have connectivity problems here is you have to get the preamble to go through. So with an OFDM system, you have to synchronize with the preamble. Okay, so the preamble doesn't go through, or you have to transmit the header information, which tells you what modulation to use, right? And so sometimes that doesn't get through. Okay, and so it's like the preamble doesn't get through. And so the connectivity wasn't so hot there, using these different bandwidths. But when we were able to scan these subbands, and the thing is that your power, you have a fixed amount of power you can put on there. Okay, so if you're using a wide bandwidth, your power in these subbands is less. But if you focus on like 42 kilohertz, you can increase the power in that band, and so that helps a lot. So we're making a proposal in the IEEE to use the subbanding right now, and so it's we're having a fight there. But the thing is, when you use subbands, your connectivity is really good. If you don't use these subbands, this is what we say, and not necessarily it's agreed with everybody. Your connectivity is not as good. And so if you only get 67% connectivity, for example, well, this is a no-go. You got to have almost 100% connectivity. You can't have people working for the utilities, contractors going out and fixing each one of these things. It would be just too costly. So there's still a lot of things to be done. Make progress here. And without just waiting until we solve all the problems. How do we make progress here without just waiting until we solve all the problems? There's standards that actually limit the power. So I can't off the top of my head tell you what the standard is, but I can find that out for you. It's related to the FCC in the United States, how much power you put on there. So, but I can find that. That's a good question. I need to know that answer. So, as you can see, it still looks like it's immature. The standards are evolving. The system will work. We know the system will work. But it's still tough and unpredictable communication channels. You have to do field trials to really understand these channels really well. And we have to achieve 100% connectivity. So what TI provides right now is the analog front-end technology, which I mentioned. And then we have a fully programmable processor for this. And so the question then always comes up, well, you got this programmable processor. It must be expensive, compared to an ASIC. But you don't want to invest $20 million in an ASIC that doesn't work, right? So how do we solve that cost problem? Well, don't wait, and don't do a full custom ASIC. And we do an application-specific MCU. So, we talk about C2000 MCUs and 430 devices. Well, I think there's many devices that come out and are all application-specific every year. So in the case of the C2000, we had special instructions to it to reduce the power and reduce the cost and make it approach the cost of an ASIC. So here's an ASIC we developed in the group for digital TV, RF on there, and it works in analog ISDBT. And we sold millions. You can see, man, we got the RF on there, and we've got the analog. We had to invest a lot, and we sold millions of these things. We need a lot more flexibility than this. And we had to invest a lot. Because this thing only did two things, but we need a lot more flexibility than this. Because this thing only did two things, DVH and ISDBT. And we understood those communication channels really well. And there was a standard that existed. So application-specific MCU, what is it? We had special instructions to accelerate certain functions. Maybe three out of all the functions take 90% of the computations. So we look at those functions, like Viterbi in particular is a really big one. FEC and FFT and some of the front-end filtering. And then we just add special instructions to speed those up. And then also security engine functions, CRC and AES and some other computations. Special transfer controllers, for example, so that the processor doesn't have to touch the data. So we add these instructions. It's not an accelerator, it's instructions that we add, and you can use those instructions. And what I found in the past is that we can compete with a custom ASIC in terms of the cost, in particular. Power not necessarily, but cost you can come up with maybe about the same die area as you would with a full ASIC. But you have full software programmability. So in a market like this, you need to have full software programmability. You still have to do experiments. We want to sell these chips to like universities or other companies and let them solve the problems, right? So we can solve some of the problems, but we don't have a huge R&D group looking at this. We want to provide the tools to other entities to help solve the problem. You're not going to do that with an ASIC. An ASIC is you have a team in your group, in your company, and you develop the chip, and that's what the customer gets. There's really nothing for a university to contribute to something like that. But this type of thing, you can fan these out. We've got this chip that exists. We're giving that chip out, EVMs, so you can do these experiments and the other analog parts. So it's a little bit of a different model than what you've been used to with broadband communications, for example, because that's totally done in the company that develops the chip, and university or other entity doesn't get an opportunity to do the experiments really. So the model is different, and people don't understand that this is like the TI model, and it's selling these kinds of products, software libraries, and then giving it to people to do the research. And not developing necessarily the end solution that you would sell turnkey to a utility or a meter manufacturer, although we do it, but typically we like others to do it. TI has about like 20,000 products and 80,000 customers, so it's a different kind of company. And not people don't understand that really. A lot of people don't. So they compare us to other companies like Qualcomm and Broadcom. It's a different kind of company. This is just the Verby butterfly. You probably know it better than me. And so the idea is you do this in 1 or 2 clock cycles in using special instructions in the C2000. And this chip exists, and we're using it now. And so you can reduce your clock rate to reduce the power, or you can keep the clock rate the same and increase the throughput. So you have a lot of flexibility. So my last slide. There's many fruitful areas. Long-term research in smart grid and power line communications, and it looks like there's still going to be lots of R&D money coming out of the government to do this kind of thing. And so I think it's a good opportunity for universities, and we'd like to, be working with you all on this stuff. And we're heavily involved in the standardization process in IEEE, ITU, and SAE, and ISO is also involved. And it's spreading us pretty thin, by the way. And then and for grid access, electric vehicle, home area network is there, but we're focused mainly on grid access and electric vehicle at this time. Medium voltage, low voltage through transformer. And I already mentioned the OFDM technologies that we're focused on. These really fit well into a TI processor, and that's one of the reasons we like them. But you also get high bit rates through a fairly simple processor. And then all these field trials we did, G3 and Prime and other proprietary OFDM versions, were done on the same hardware. So we just load different software in it to do the field trial. And okay, so for certain type of applications like solar, communicating from a solar panel might be simpler. You could do it with a lot cheaper implementation, but we have a range of these processors that can be used. That can be really low cost. And then I don't want to be making a sales pitch here, but it sort of comes out that way, but that wasn't the intent. Mainly it was to tell you what the problems are and what the opportunities are, and then, oh, well, here's something that you can use that we can give you to help you work in this area. And I can't help but to get caught up in the competitive stuff, but I try not to do that, especially in a meeting like this. And then application-specific MCUs, I think this is a good alternative to ASICs, where you might have a dedicated set of functions implemented in accelerators. I mean, that's another approach that we always look at too. And we'd like to separate the analog from the digital to allow for flexibility and time to market. And then at some point, if you have a standard that and you're going to sell 1 million or 10 million of these things, then you can always integrate the analog with the digital. And we can scale the bandwidth and the frequencies, but really the most important thing is the last bullet, and that's the University of Illinois can really help all make this happen. So thank you very much for your attention, and if there's any questions, I guess we have a couple minutes. Okay.
Do you get coupling from the wireless into the power lines, or the other way around?
So the broadband technology, I might not be answering it, but no, the wireless, we haven't seen wireless coupling. And the wireless is up around 2.4 gigahertz, right? So we hadn't really seen that, and that's pretty low power stuff anyway. As far as the emissions from the power line out, there's been studies, the broadband power line that communication technology that operates about 2 to 30 megahertz. That'll couple into VDSL and force you to put your boxes closer to the homes. And so you have to deploy a lot more boxes if you have broadband PLC out there, which they don't really put it out there much now. So I would be more concerned not so much about wireless coupling in, but PLC coupling into out the emitter into other wireline type technologies. Yeah.
When you're talking about the standardization of PLC, is that with the smart grid people together, or?
So, okay, so smart grid is sort of a broad term, right? And so NIST is in the United States, and they have they've been given responsibility for the smart grid.
Standardization.
Selecting the standards.
Okay.
So they're not actually doing the standards, but they're selecting the standards that they approve in the United States.
And
IEEE, I'd have to go back and look at the most recent list. It's been in and out, but it should be the IEEE P1901.2 ought to be there at some point once we have that document finished. And then P1901 is the broadband is in there, and I believe. And then the ITU, and so we just have to go to that website and look at what the approved standards are. And this is an ongoing thing, and with NIST they have these study groups like PAP 15 they call it, and they're looking at coexistence between different power line technologies and interoperability. So this is an ongoing study.
So when I read the various video or whatever, and then they're talking about smart grid standardization, PLC is part of that, but oftentimes they don't say PLC.
That's right, yeah. But you have to look at the list of standards, and then you'll see the PLC standards appearing there.
I see.
Yeah,
Thank you.
yeah.
You say there's a lot of scope for research here. Are you saying there's a lot of variation in channel models and you need to come up with communication schemes for these models? Is that what you mean by research on?
So that's one of them. The other one is networking. I think it's a very complex network problem where you have the meters disappearing and appearing, and you know, your quality metrics. You have to have link quality metrics so that your router can determine the best route to a meter, because it might have to jump through multiple other meters to get there. So I think networking is a fruitful area too. So that type of thing, and then the modem itself, that technology is, I think it's a fruitful area. Just understanding that communication channel. I don't see much. Yeah.
Is there diversity of paths to a meter?
Could be.
So to my home, there are many paths coming.
Could be. If with the RF mesh, there could be.
Over the
Yeah.
RF.
Oh, but this is the same. So this is similar, not the same, but it's similar. So the power line is similar because there's hidden nodes. You can't see everything from the concentrator. So you have to just form this mesh to be able to get to every endpoint, every meter. You're not going to get connectivity for 100% directly from the concentrator. So it's the same thing as a mesh, RF mesh. It's different because it's a different kind of physical medium, right? But it's sort of the same kind of problem, I think. But the link quality metrics, we have to identify, well, what are those link quality metrics? And then how fast can we form the mesh? If it takes 3 days to form the mesh, that's no good, for example. And then when an endpoint disappears, how quickly can you reconfigure the mesh transparently to the system? And it has to be done quick. So those are areas, I think, of some good research.
So that sounds like peer-to-peer networking or something else?
Well, I mean, it's peer-to-peer, but you mainly have one concentrator node in these networks, but it's sort of peer-to-peer. Yeah. I mean, for G3, the MAC is based on 802.15.4. That's the RF 2.4 gigahertz MAC. But then there's the MAC doesn't do all the the routing, that's above the MAC, and so I'm really talking about above the MAC. And then what does the MAC give this router, our Ripple or whatever you use? That's one of them, and load is another one. And to do so that it can do a fast, efficient job in forming this network. And then the subbands is another thing. So how do you use subbands? Let's assume that subbands are required, and so we have to scan that this 500 kilohertz band, just as an example, with these 42 kilohertz subbands, and then we have to do it quickly, and so find the best subband to talk to the meter from a concentrator or a node in the network, and not take a year to do it. And so that's another area, I think. I think there's lots of areas here. And so, we focused a lot on wireless in our group, and we did a lot of ADSL work, and we did cable modem work. The channels are not easy, but compared to this, they are easy. And because we understand them, we've got good channel models. We can use the channel models in our MATLAB simulations. We can go to standards meetings and we can compare results. This is still, a little bit open. So as long as I think we're putting resources into power grids, smart grid, then this is a good area of research, and especially with the government funding, I think, that we're getting now. I mean, I would say there's lots of nice problems there to solve. Any more questions? Okay. Well, thanks a lot.